Okay. So I think last week we were we have discussed quantum functions, right? So they were different layers of ideas. So we have first quantum bit, right? That's the most fundamental unit. And then we have quantum gate. Yep. So quantum gate is what you use to manipulate quantum bit. So this is also called qubit. And then we talk about quantum circuit. Yeah. So we put a bunch of quantum gate together as quantum circuit. Right? All right. And then there's another layer of complexity. It's called quantum processor, or I would rather call it with a more specific name, quantum function. Okay, quantum processor could be like the entire hardware, but the quantum function, and that is basically an architecture that is designed to achieve certain purpose. Okay, and then today we will talk about quantum algorithm. Yeah. Now, um, I want to start by first mentioning that all the uh, physical process that we use to um, manipulate quantum bit is through the Hamiltonian, right? They are all included in the Hamiltonian, one form or the other, okay? And which basically consists of, if it's a two-level atom or two-level system, then it will be consist of the raising lowering operator of the Pauli matrix. And if it's a continuous variable system, like harmonic oscillator or photon, then we will have raising and lowering operator, right? Okay, so basically Hamiltonian is made of these operators, and they are typically, if they are from a physical process, they are typically arranged in a way so that the Hamiltonian operator itself is Hermitian. Okay, so that's no problem. So Hermitian, and Hermitian implies that all the observable associated with the operator is real number. Okay, so that's one implication of it. Another implication is that, so the first implication is observables, or you can call eigenvalues, right, of, of the Hamiltonian is real. Okay, so that's the first thing. Second thing is the propagator, the quantum propagator, propagator. Is that right? Proper, yeah. Propagator. Propagate, right? A propagator, which is used to evolve the quantum, sorry, the wave function or the quantum state. The propagator has a general form. So by the way, this is typically, we don't really care about the unperturbed one because they just provide the resonance condition. What we care about, what we use to manipulate the unperturbed systems, the interaction Hamiltonian. So this propagator usually has the form of interaction, right? And this is just like a general, pretty much like a general solution of the Schrödinger equation. Okay, of course you need to expand this exponential to have an idea of what it does to the quantum state. So, but anyway, having been able to write it in this form already give us a lot of information, because from this form, we know that the Hermitian property of the Hamiltonian necessarily imply that the propagator is unitary. Okay, propagator is unitary. Unitary, okay? Why? Because, okay, so this is the conjugate of it, right? And when we have the conjugate, this operator becomes this. Yeah? And the Hermitian condition allow us to make this into this. Sorry. Yep. And if we multiply this with that, they canceled, right? But I want to warn you that so there is this thing. So when you have two when you have two it is very tempting to think, yes, the, the multiplication just leads to summation. That's true for scalars, but for operators, we have an additional term here. We have an additional term here. Okay, we have the commutator, right? Okay, so this only works if the operator commute A and B and commute. And in our case, it does because it is just itself, right? So we can safely put this together with this, and that will be 0. So this will give us unity, identity, right? And thus this proves the unitary condition, which means the conjugate is the inverse operation itself. Yeah. All right. So that's what we have to say about quantum gate, right? Okay, because quantum gate are from physical process that are Hermitian, and quantum gate are usually in the form of propagators, and propagators are unitary. So quantum gates are unitary, and unitary also means it's one to one. It's one-to-one mapping. Okay, unitary also imply one-to-one mapping. Why? One-to-one mapping means if you have an input, and then right, you give this, and then you have a value, right? Now, if you take the value and you apply an operation, not the original operation, but the inverse operation, right? So in other words, you run the entire machine backward, okay? Sort of like that. Backward is not like a really accurate term, but you know what I mean? So if you operate on the output state with an inverse operation, then this will necessarily give you the original input. This means one-to-one mapping, right? Because you can only use this to find that and that to find this. They are like in one-to-one mapped. And of course, this can be easily proved, right? So something like this. So if you apply an inverse operation on this state, and that will give you this. And this is just identity operation. Actually, it doesn't even require the unitary condition uh, to, to make it one-to-one mapping. This yeah, this is as long as your inverse operator exists, that will work. Okay. And right, so if there exists an inverse operation, then it is one-to-one mapping. And of course, for unitary operators, of course, there exists an inverse operation because that's just the conjugate of the propagator itself. Okay, now I have a little more things to say about this thing, right? Because now you see, basically, since all quantum gates or all quantum operation, quantum manipulations are unitary, thus necessarily there exists an inverse operator. We call this reversible. Okay. So quantum operations are reversible. And reversible simply means the inverse operation exists. Okay? Okay. Quantum operations are all reversible, are always reversible. But classical operations, or maybe I should say quantum gates, okay? Okay, let me just be more specific on gates. Classical gates are not always okay. Why do I say that? Because we see that the most classic gate is the NOT gate and the AND gate, right? Yeah. So NOT gate has the truth table of this is in, this is out, right? If you have 0, 1, you have 0, 0, you have 1, right? So there's apparently a one-to-one mapping, and one-to-one mapping and reversible is equivalent to reversibility. Okay, so this is reversible. This is one-to-one mapping, so this is reversible. But for AND, right? AND is a two-bit operation, so you need to have 3 columns, right? And this is in 1, and this is in 2, and this is out, right? So we have 1, 0, this is 0, 0, 1, this is 0, 1, 1, this is 1, 0, 0, this is 1, right?
0.
Really?
Yeah, 0, 0, 0.
Oh, yeah, thank you. Right? So we see that 0, there are 3, 1, 2, 3, 3 inputs that map to 0. Therefore, if you operate on, if you have like a function or something that operate on 0, right? You cannot, it will be like 1 to many.
Also, reduced dimensions also means 2 input, 1 output, right?
Hmm?
Also, it reduces dimension, so most likely.
Right, yeah. Right.
Because 2 input, 1 output.
Reduced dimension, correct. You can also say that information is lost, and because they are destroyed or replaced, and this also has to do with, entropy of quantum information, energy dissipation, that kind of stuff. Okay, but for here we just know that this is irreversible. Okay? So therefore, we see that to build a quantum computer, it is not so straightforward that we just copy everything that we have in the classical computer and move it to quantum computer, because obviously this construction couldn't work for quantum computers. Okay? So we need to take special note of this reversibility of quantum gates, and when we design gates, we need to take that into account. What we typically would do is if we want to build an AND gate for quantum gates, what we will do is we will find a reversible version of the classical gate. And in this case of AND gate, I believe we have this thing called Toffoli gate. And this takes a three-bit input. So instead of 2, we have 1, 2, 3. So in 1, in 2, and in 3, and we have this out. Okay? Is it
only one output change, but there is 3 output, right?
3? Sure, right. Yeah. Yes.
The last one flips, but
yeah. Okay.
Yeah,
you're right, because this is reversible, and thus you need to keep all the bit information. That's correct. So output
so
1.
All those information we can reverse it.
Right? What?
Only with all the information we can reverse it.
That's correct. Right. Yeah. So this will have 3 input and 3 output. Okay. What we typically would do is we will first build a reversible version of the classical gate, and then we'll implement this construction with the quantum operators, and thus have like a corresponding quantum gate for certain classical gates. Okay, so that's like an important layer of complication when we think about quantum computation. There are just this fundamental issues that we need to deal with first, and before we move on to build to have like physical implementation of different layers of quantum processor. Okay, and of course this is the subject of study in, for example, computer scientists. A lot of mathematicians and scientists, they study things like this. Okay, not necessarily physicists, but like a lot of people who know much better about math, study this kind of stuff. All right, so that's this thing I want to bring up. Okay, and so and circuits are just multiple gates put together in series, concocted, as they say. Now, what about quantum function? What is the difference between quantum function and quantum gate? We know gate is kind of mapping, right? You take this input, 1 qubit, 2 qubit, 3 qubit, you name it, and then the gate give you a mapping, and the mapping will give you like a result, right? So what is quantum function? How is that different from quantum gates, right? I think that's a confusing point, and we want to highlight that quantum function is basically the quantum. So unlike quantum gates, which are just by itself gates, operations put together using Hamiltonians, quantum functions are quantum version of classical function. Okay? So there, when we talk about quantum function, we're really talking about like a quantum mechanical realization of the same classical function that we used in classical computers. And since there are like features, physical features belonging to the classical computers. It also, these features also carried to the classical function. Okay, for example, you have this classic example. This is this constant function. Okay, this is one of the most simple function that you can think of when you think about classical function. So whatever input you give to the function, it always give you the same output, constant. Okay, and this constant could be any number, 1, 2, 3, 4, 5, 0. Okay, so this is a pretty one of the most simplistic classical function. Now, and of course there are a lot more, but the point here is that when we, whatever classical function that we have in classical computer, because this is how we operate, right? We operate, we use classical computer for a lot of other things, and we want to build a quantum computer that can do the same thing as we have done with classical computer, but much faster, supposedly. So it is supposed to reproduce every, it's supposed to encompass every capacities that the classical computer has. Therefore, all the classical functions, we should be able to generate or evaluate, or what we should be able to realize with the quantum computer, right? So this is like our goal, to be able to execute the classical functions on a quantum computer with a faster speed, or better scalability. That was the goal. Therefore, we must have a construction that we must give special construction so that this can be satisfied. And when we talk about classical constant functions, we see that this has this feature of many to one, right? Like this is one of the most noticeable feature of this constant classical function. And since quantum gates are necessarily one to one, we cannot use a quantum gate. We cannot use a quantum gate to realize this constant function. Right? Agree? We cannot use a quantum gate to realize this constant function. Therefore, there needs to be additional construction involved, in addition to just the quantum gate. There needs to be additional construction involved in order to make this happen with quantum mechanics. Okay, and last week we've talked about this kind of function, this kind of operation simply cannot work. Simply cannot work because the unitary, by the way, whatever the function is, it is still made of the quantum gates. So if quantum gates are unitary, the function is also unitary. Now, the tricky part is, if unitary operations are one-to-one mapping, how can we ever realize this many-to-one mapping with unitary operations? That's like the saddle point here, okay? And now, so it turns out the key is in the construction, okay? And last week we talked about why such a simplistic construction wouldn't work. This single qubit input and single qubit output construction wouldn't work, because the unitary operation of this function will necessarily lead to the inner product of the output being preserved. So if you have A and B, and you have separately, FA, FB, then the inner product of FA, FB should be the same as the inner product of A and B, right? But this fact, this consequence of the unitary operation is in contradiction with this magnitude 1 condition. Therefore, this construction simply just cannot work for constant functions. The minimum construction that needs to happen is to have 2-qubit input, and your output also needs to be pretty specific. Okay, your output needs to be the function, whatever classical function that you have, the function, take this input and the sum modulus 2 with this, okay? This is what we call the control qubit, and this is what we call the target qubit. Okay, yeah. All right, now, so with this minimum construction, we know that we can like this, like the bare minimum for quantum function in order to realize all classical functions. Okay. Now next thing we want to talk about is quantum algorithm. Okay, quantum algorithm is like the highest layer of all this. Okay, and quantum algorithms are
quantum function is just like a subpart of quantum circuit, right? Or the whole quantum circuit or a portion of quantum circuit, right?
Quantum circuit is more of like a hardware term. Okay.
No, it's a collection of gates, right?
Yeah. But a circuit, you can have a circuit, yeah, but it doesn't serve as a function.
Yeah, but all quantum functions are quantum circuits, right?
Are made of quantum circuits, correct? Yeah.
So it's like a subpart.
It's just a hierarchies. Yeah. Okay, hierarchies.
So we can have like multiple quantum functions stack up a huge quantum circuit, right?
No. You can have multiple quantum functions in an algorithm.
Yeah, but that algorithm itself created.
Of course, yeah, you can call anything a circuit. Yeah, but that are like the minimum definition of circuit is a series of gates put together. Okay, when you work with this minimum, not a general definition, but this minimum definition of quantum circuit, then you soon will see that quantum circuit is not equal to quantum function. But quantum function is a larger set. Quantum circuit is a subset. Okay, because quantum circuit, for example, you will put 2 gates together, right? Does this do 1-to-1 mapping only? Yes. I mean, I can do this, and then I can have a single qubit input and a single qubit output, right? This will definitely do 1-to-1 mapping.
So it should be the opposite, right?
Can this be used as a quantum function? No, because we talk about quantum function needs to have this minimum construction of this.
So quantum gate is bigger set, right?
Huh?
Quantum gate is the bigger set, right?
I don't like to talk about sets because this is not I like to talk about building blocks.
Yeah, but you just.
So what I write there is the building block from bottom to top.
I mean, like you now mentioned, like quantum function has the bigger set, like that you just mentioned.
All right. Okay.
Yeah,
I was wrong. I didn't mean set. I mean it just like a more complex layer.
A little more complexity should be there.
Yeah,
As you
more
just
complexity is involved in quantum function than for the bare minimum of quantum function is more complex than the bare minimum of a quantum circuit. That's what I mean. Okay, so I was talking about a hierarchy of complication. Okay, now the highest one is quantum algorithm. Okay, and quantum algorithm, you can think of it as recipe. Okay, when we think about recipe, we ask the question, what's the recipe for, right? Is this recipe for a drink? Is this recipe for an ice cream, a special flavor of ice cream? Is this recipe for like maybe some cake, right? We ask when we talk about recipe, it is always pointing to a problem that it is designed to solve, right? So the goal of the recipe is to make cake. The goal of the algorithm is to solve a problem. So to understand quantum algorithm, we need to understand first the problem. Otherwise, it doesn't make sense. Yeah. Now, in order to solve a problem, so this is like in high schools we have a problem, and like you're asked to calculate how much gas you need to use if you want to drive from the East Coast to the West Coast in, I don't know, 3 hours. So how fast you need to drive and how much energy that was going to take. Okay, so when you try to solve a problem, there are a lot of things that you use, a lot of tools you invoke to 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 attack this problem. Okay, so quantum algorithm is the highest layer in this hierarchy of complexity because it is designed to solve a problem, and you need all the tools you can get, all the weapons you can get in order to solve this problem. So we first need to understand what's the problem to be solved. Okay, and by the way, so this is just like at the conceptual level, I call it recipe, but at the physical level, I call it construction. Construction. So algorithm is a certain configuration or certain constructions of different gates, different function all put together. Like you have this construction, and this construction will allow you to solve this problem. Okay. Now it turns out the problem that we can solve, we can meaningfully solve with quantum computations, is actually quite limited. Okay, it's not like we can use it to browse the internet and watch YouTube. It's not like they can do everything. Okay, so there are classes of problems that are suited for quantum computation. So number one, we need to understand that quantum computation is not meant to replace classical computers and just make you do everything much faster. That's a very common misconception. They just think quantum computers are faster and more powerful and better than supercomputer. Therefore, we want to spend money on it. No, that's not the case. It only solves a finite number of classes of problems. And if the problems that it can meaningfully solve through quantum computation is finite, if the number of the problem is finite, you can imagine that the algorithm are also finite. There are actually just a handful of algorithms that people have already have been able to come up with. Okay, and so that's today we want to talk about Deutsch's algorithm. That is the simplest or the minimum build of quantum uh, that's the minimum build of quantum computation that use the quantum that demonstrate the quantum advantage in computation. Okay, and it is not super complex, so we should be able to cover it pretty quickly. And Deutsch Joe's algorithm is just a generalization of this, so that won't take much time. And optical implementation will take a little more time, but that is mainly to give you an idea of how the algorithm is physically realized. Once you know how it's physically realized in one system, it will not be so hard to think about how to realize it in another system. And here we choose to use the simplest construction, simplest system, which is the optical system. Okay. And another reason is because our lab is equipped with equipments that can do this. Okay, and that's why we talk about this. All right, but before we jump into Deutsch algorithm, we want to ask first one thing: how, where is quantum computation meaningful? Asking that question means implies what is the necessity of quantum computation? If I can already do everything with classical computations, yeah, maybe it takes more time, but there's nothing I cannot do with quantum with quantum or classical computation that I can do with quantum computation. If both methods give me the same outcome but just different, it just take different time, it won't matter so much. It's not worth investing billions and billions of dollars, US dollars, into this industry just to have a little bit of speed up, right? So, what is the purpose of quantum computation? What justifies it? That is the question that a lot of people miss. When I think about quantum computation, I think about, oh yeah, you have superpositions of qubits, therefore you can do parallel computing, and that just by default much faster. Okay, everything boils down to speed. Well, maybe so, but it's not in a straightforward way. Okay, we want to illustrate this with an example, right? And this example is the problem for Deutsch algorithm. Okay, so suppose we have classical bits, right? And we have, say, 100 numbers. How many bits do we need? How many bits, like the minimum number of bits we need to express all the numbers from 1 or from 0 to 100? To answer that question, we of course use the binary coding, right? So 0 is 2, 0, right? So this gives you 1, 0. So 1 digit, right? And let's just work on it a little bit. So 0, we just give a little more, a few examples, 5 and 10 and 64 and 100. All right? Okay, so I'm just gonna use this to illustrate the point. So this the binary coding for this is 0. The binary coding for this is 1, 0. So it takes two bits to express this number 2. And what's this?
101.
101. Thank you. And what is this?
1010.
Agree? Okay. Yeah, we all know how this works, right? This is just 2, 0, and this is 2, 1 plus 2, 0, and this is 2, 2, 2 plus
2 0. In the second case, there is no 2 0
right.
because its coefficient is 0.
Mm-hmm. Yeah. Okay, so maybe I should do this.
No, that's okay. But if the coefficient is 1, you put 2 power that.
Uh-huh.
If coefficient is 0, you multiply that with 0, so that term will be gone.
Yeah.
So in the second one, the 2 power 0 is not there.
Okay.
Here, 2 power 0 will be there.
Oh, I see. So this is more like a multiplier?
Yeah.
Okay.
Multiply that with.
So maybe I should just write. Okay. I see.
In the first case also 2
Okay,
power
yeah.
0 into 0.
0 times 2, 1, right? This is the first digit.
0.
Okay, let me see if this I have this right. This is the second digit.
No. It is first is 0, right? 2 power 0 is 1, right?
Oh. Oh.
Yeah, exactly. 2 power 0.
Yeah.
1. 0.
Yeah. Right. This is sorry. And 0. Sorry. Yeah. This is the first digit. This is 0th digit. This is the first digit, right? Okay. And this is the second digit. 0. First digit. 1. Right?
Yes.
Okay. And this is the fourth digit.
Third.
Oh, sorry, third digit. 0, second 1, 1.
8 plus 2.
Right? So this is 8 plus 2. This is 10. Okay. How about 64?
It's 1 0 0 0.
1 0 0 0. So 1 5. Yeah, 5. And this is 0 0 0.
No, I think that there is one more 0, I think.
This is 1 more 0?
Yeah.
Okay, thank you. 0 0. 1 2 3 4 5 6. 6 digits, right? And this is 8 32 64. Yeah?
Yes.
Okay. So 100 is not from this number, right? We just need to add 32. So 1 1, right? So this give 64 and this give 32, right?
Yes. 96.
So 64 32 we have 4, right?
Yeah.
4 this will give us 4, right? So this is 0 1, this will give us 4, and 0 0 100, right? So this is 1 1 0 1 0 0, right? 1 0 1 0 0. Yeah. So okay, highlighting this because not everybody's like you, very smart and good at binary systems. Okay. I'm not good at binary systems. I can barely do it. Okay, but the point is, you see, this requires, if you want to write the number from 0 to 1, if you want to cover the number from 0 to 100, you need to have at least 6 qubits. Okay, and so this is 6-bit. Okay, so this is for classical computation. And if we want to do quantum computing that covers numbers from 0 to 100, right? We also need 6 qubit, right? Why can't we use superposition state to represent a number? Why can't we do that? We cannot, because we talked about this last time, because when you do a measurement, right? When you do a measurement, it always collapses to the basis state.
Yeah, but we do multiple measurements, right?
Hmm?
We do multiple
Right,
measurements.
but if you want this to be measurable, this number to be measurable, you want to like measure 64, you want to measure 89, right? This, they must correspond to a basis state. Because the measurement collapse whatever superposition you have to one of the basis state. So if the basis state does not represent, if the number is not represented by a basis state, you never show up. It will never show up in your measurement. Okay, so that's the reason we talked about this last time. We cannot use superposition state to do like to act as quantum registers. Okay. All right. But so 6 classical bit and this also requires 6 quantum bit qubit. Now, the space, so the mathematical space, or the number of basis state, okay, that's what I mean, basis, of 6 bit is usually, so for two bit, for one qubit, the mathematical space is this, to the power of 1, okay? If you have 2 bit, right, the mathematical space is to the power of 2, right? This means you have 0, 0, 0, 1, 1, 0, and 1, 1, right? So you have this to the power of 2 give you four elements. So this is 4 elements. We talked about this also last time, okay? So a 6-bit or 6 qubit set or 6 qubit space will contain how many basis states?
6.
Yeah.
124, 128.
To the power of 6, right?
Yes.
Okay. And this will be,
128.
yeah. So we have 128 numbers of possible measurement outcomes. Okay. And that's like how much number we have at hand. All right. Now, if we want to,
I can think of some ways to make means like five means if you want to denote 5, I can think of some ways to use that superposition and get that. If I'm using multiple shorts, then I can make it such that like if the probability of 1 is like okay, probability of 1 is just for like the hundreds. I'm like, okay, if the probability is 1, it's 100, 0 is 0, and if it is 0.1, it's 10, 0.01, it's 1. If I denote like that and create the state, then if I'm doing like 10,000 shots, I'll get the probability of 1, and I can say, okay, this was the state. So I can decide for something, but the method of addition.
But you're not using a superposition to represent a number, do you?
In that case, we are using superposition to
represent numbers.
Yes. For example, like just like if we have the state 0, alpha 0 plus beta 1.
Yeah.
So alpha, I'm taking what's the beta square value. What I can find that by multiple shots.
Okay.
So what's the beta square value into 100 is my number. I can imagine like that. If I'm putting 5, I will have beta square equal to 0.05. If I design such that whenever I have beta star 0.05, I get 5. So I can create a state like that. If I can store that state multiple times and produce, I can get 5.
But then your measurement,
I have to do multiple shots,
okay,
but I don't need multiple qubits as register. I just need one qubit with a superposition. So it is possible, but to do computation using that, only some specific computations I can use that. There are a lot of risks.
I'm just thinking about the measurement that you perform.
Measurement, either I get 0 or 1.
Right.
But I'm doing multiple times. So I'm getting multiple zeros and 1. I'm adding all the ones I got. Like if I'm doing
Then how?
100,000 shots.
So if you have an input of, say,
for example, if I create one qubit like this, so this is like, this is 0, this is 1, and this is probability of 1 will be 0.25 for this case.
Yeah.
So I'm creating this qubit as like 5. If
Yeah.
it's 0, then 0, 0.25, then it's 1.5, it's 2,
Yeah.
0.75, 3,
Uh-huh.
1, it's 4.
Sure.
I'm saying, okay,
Yeah.
this is, if it's here, I take it as 0. If it's this,
Right.
I can define it like that.
Right.
So if I take this one state, but I'm doing like multiple shots, I'll get 1.
You mean show algorithm,
0,
right?
1, 1, 0.
You mean
like
show algorithm, right?
Hmm?
You mean short algorithm?
No, I don't
Short.
need it.
What do you mean by short? Multiple short.
Short means we are measuring it multiple times.
Shots.
Shots.
Like trials.
Yes.
Okay.
Because in quantum computer, like we do multiple shots to get the final results. Right?
Okay.
Single shot we'll get 1 or 0. So to get the probability we need to do multiple shots of this same state.
Okay.
So if I get such like this, what I do is I can get the probability chart of 0, 1. So I'll get.
Sure.
This should add up to 100%.
Yeah.
So with this, I can measure, okay, where it is point, and that pointing, if I map such that I can, in theory, make circuit like the higher classical bits in
Okay, I see.
bits.
I see. So the measurement you're talking about is
measurement always give me 0 or 1.
Right. A probabilistic outcome. Okay, so this will probably have to do with like probabilistic computation.
Yeah.
Right. You to get an outcome with a certain input, you need to run it multiple times in order to know
all
the outcome.
Quantum computer has to do that, right? There is
sure, but okay.
There isn't any like.
But
even
for
like
quantum memories,
ion trap quantum computer use it.
But for quantum memories,
like
if you want to inquire what is stored,
that like, but that even with like 6, if you take 100 with 6, we cannot get the exact this.
Right.
Because sometimes instead of 1 here, it will give 0 in quantum case. Right?
Well, yeah, that is just errors.
Not only error means if it's exactly here.
If it's in the basis state, then you inquire only once, and you always always give you the same result, right?
So in that case, we are treating it as classical, right?
Right. Yeah. yeah, but okay, now right now my point is we want to do something that classical computer can do, but we don't want to do it better. Need to have like sort of merits attached to it. We want to be able to do it better, either faster or more scalable, whatever. We need to do it better. Okay. So if I just want to inquire, if I have like a memory, and that memory represent like certain information, right? And then using classical computer, I can inquire it once, and then give me an outcome. But using quantum computer, I need to like inquire 1,000 times to give me an outcome. That is not an advantage.
Yes.
And that kind of defeat the purpose.
No, but,
okay, that defeat the purpose just for this task.
yes.
It defeats the purpose. Of course, you can do it another way, but it's not better. It's not a better way. No, it's not just not a better way. If you need to, for example, two, right? For classical construction, I have this, right? I store it as this. Somehow I store it as this, and now I want to inquire it. I want to know, like my friend Tom, my friend John, stored this number last night in the computer. Now I come in the morning, I want to take a look at it, right? I inquire once, it gives me two, right? But if you want to do this with the quantum memory or quantum computer you had, I have to do it multiple times, maybe like 100 times, in order to have the probability to see the distribution, to see the ratio, and then I can determine, oh yeah, he stored 0.5 instead of 0.25 or 0.75. The resource it takes to do the same task is more in this case if you do it quantum mechanically. Therefore, it defeats the purpose of quantum computation. Quantum computation and so for quantum computation, our goal is to do the same thing better. Whatever we can do with classical computer, we want to be able to do with quantum computer, but better. And we even want to do the things that classical computer cannot do. That's the whole campaign, that's the whole idea of quantum computations, right? So let me just stick with this construction that, if we want to inquire states, we want to do it as well as the classical way to do it, which is like only one inquiry will give us the number. And in this case, one inquiry, if one measurement will give us the number, then that number must correspond to a basis state. Okay, so we agreeing with that on that. Okay, so in terms of inquiry, we are not doing better than classical computer, but we're not doing worse than classical computer. Same performance. Okay. Now, the next problem is, okay, so besides the inquiry, besides of the inquiry, we also are interested to find. So we want to do like one step. We want to go one step further. Now we are interested to find an arbitrary function, exponential function, logarithmic function, trigonometry functions, whatever function you can think of. Okay, even tangent times cosine times exponential, whatever function you can construct, right? We want to know, and this is a hypothetical problem that David Deutsch came up with. So we want to know whatever classical function that we have at hand. We want to know a global property of this function. Okay? Global property of this classical function. Sorry. Right. Of the classical function. We want to know some global property of the classical function f of x. Okay? Oh, by the way, of course, we can go one step back. We can ask, actually, let me just do it this way. Let me do it local property, okay? Local property means, I have this set of, I have this six qubit space. I have this set of 128 numbers of basis state, right? Okay. And then I want to know how does the function evaluate here, or here, or here, or here. This is what I call the local property. I want to know the local value. Okay, so I want to know, for example, F89. Okay, I want to know F55. Okay, so these are called the local property. How can I do this with classical computers? Of course. I mean, it's a classical function. Can I do this with quantum computers? Answer is yes. You can do it, right? How do you do it? Well, we need to use an extended version of this construction that we have, right? So this is the quantum. Yeah. So this is the function evaluate at input x. So this is your input, your primary input, and this just belong to part of the quantum construction. And your output state is this. Okay. Okay. So can we evaluate f of x, f of 55? Of course, here x needs to be not a single bit. It needs to be probably 1, 2, 3, 4, 5 bit, 5 qubit state, a 5 qubit state, right? Okay, and 89 will be a 6 qubit state. Okay, so this needs to increase, and so this needs to be extended. But sure, we can evaluate it. So no problem, we can do that. We can find out what the functional value is for this classical function. Are we doing a better job than classical computers in this case? Answer is no. I mean, classical computers, you input 89, it gives you an output. Here you also input 89, it gives you an output. We're doing it in the same at the same performance, just like this case when we were inquiry, the stored memory, they're doing the same. They do the same. The performance is the same. Okay, so we know that both memory inquiry, both memory inquiry and local property of classical function, we have the same performance for classical computer and quantum computers. Okay, now how about global property? Okay, what do I mean by global property? Of the, so this is first thing, second thing. Out. Okay, let me just. In. Okay, global property of the classical function. Okay, what do I mean by that? I mean something like this. Do I have the mapping? Do I have all the mapping to the? So there is, and it's not limited to this, but this is is, for example, do I have a constant function, constant mapping, okay? Or do I have a balanced mapping? And of course, there are other possibilities. But if I want to ask these two questions, if if the function is limited to, for example, 6 to, okay, my output is limited to a single qubit, right? I can have all the basis states mapped to the same qubit state, 0 or 1, right? Or I can have half of them, which is 64 of them mapped to 0 and 64 of them mapped to 1, right? So this is the problem that I want to consider. I want to find a global property. It's like the parity of the function, the negativity of the function, like it is a global property. And how do you find out about the global property of a classical function? In a classical computer, what you need to do is you need to exhaust all the possibilities. You need to evaluate first f equals 0, f of 0, and see which one you map to. And then you map and you evaluate f of 1, f of 2, f of 3. You need to exhaust all the possibilities. And then you just keep counting, and then you finally see if this has the same number as this, or if this has all the votes. Okay? So how many rounds do we need to do with classical computer if we want to? So this is the problem for the Deutsch algorithm. Okay? If we want to find out which of this global property the classical function has, a balanced mapping or constant mapping, how many rounds do we need in this case for classical computer? 128 times, right? 128 times for classical computers, because we need to exhaust all the possibilities, all the basis state, or all the computational basis. But how many times we need to run with a quantum computer to find out the global property, which one it has? 64, 32, 16? How many times? Not sure. 100, certainly 128 times will do the job. Certainly, right? Because this is just the same as your local evaluations. You evaluate this also 128 times, and then you just fit in different basis state and then see what's the outcome, right? Using the quantum computer, and you will just achieve the same performance as the classical computer, right? That we can certainly do, but can we do better? Okay, so like that kind of method is one algorithm, but that kind of algorithm does not demonstrate the quantum advantage. It does not show any improved performance. Quantum advantage means improved performance. All right. So if we just do this local evaluation, then this algorithm does not show any quantum advantage. Can we come up with an algorithm that demonstrates that leverage with whatever superpower the quantum computer has and demonstrate quantum advantage in this problem? The answer is yes. In this specific problem, we have the Deutsch Joza algorithm to use. And if we use the Deutsch Joza algorithm, then the answer is 1 time. Okay? Quantum computer. If we applied Deutsch Joza algorithm, Yeah, just 1 ton. And you see, if we increase our computational space to say 10, 10 bit, right? This goes exponentially up, right? So this goes 2 times 2 to the power of 10 times. But quantum computer, the Deutsch algorithm, still takes 1 ton, 1 run. Or maybe I should say ton. I should say wrong. Okay. 128 runs and 1 run. It still takes 1 run to find out whether this classical function is constant mapping or balanced mapping. Okay. So how does it exactly do this? We will explain this with examples in the second half of the lecture. And right now, let's take a little break. Okay.
One thing I didn't understand now is Deutsch algorithm is the classical one which need 128 runs.
Say again.
Deutsch algorithm is the classical case which need 128 runs.
No, it's the quantum case.
But you said Deutsch, Josche is the case which need 1 run, right? So what is the Deutsch? Just the Deutsch one.
The Deutsch. Okay. The difference is your input. Your input. Your input. The difference is in the computational space. So this has the computational space of 1. So 1 qubit. Okay. One digit. Okay. Maybe I should say this is for 1 digit, 1 bit, or 1 qubit register. Okay. And this is for n bit register. So they are the same thing, just the size of your register is different. Okay. So I mean, for Deutsch, if the register is limited to a single bit, right? Then you have two numbers, and the classical computer will take two runs, and the quantum computer will take one run, right? Yeah, it's better, but not so impressive. Okay, that's why it is. After, I mean, it is like a proof of principle demonstration that this is doing better than that, but this is still not very impressive. So then Joseph came along and generalized the algorithm so that it can handle n qubit register. So when you scale this up, right, the resource it takes, the time resource it takes, grows exponentially. But the quantum computer still remain one, and that is impressive, and that clearly demonstrate the quantum advantage. With Deutsch algorithm, it kind of demonstrate the quantum advantage, but not really, not like so practical. But with the Deutsch Jaws algorithm, yeah, we see that it does have this one versus exponential growth of of resources that you need. It does have this improved performance, right? If the classical computer the time it takes for the classical computer to run grows exponentially, while quantum computer can do it in one run, we can also say that the quantum computer speed grows is scales exponentially faster. You can use this as like a base, and this you use this to compare that. And if the time it takes is exponentially large, then the speed it takes here is exponentially faster. Okay, you can say it either way. Okay, all right. Are we good? Can we start? Okay, great. So the Deutsch construction involved the following. Of course, you need a function. Okay, that function is, I mean, we want to evaluate the classical function, right? So we have to start with the function, and the minimum construction of a function is this, right? Is this x, y, the unitary operation or the propagator that represent whatever gates you put together to achieve this function mapping, okay? But your input and output needs to be in a special configuration, okay? That's the key. And y, so y, okay? So that's the function. So this is the function. What?
Top right is x or y? X, right?
X, yeah. Oh, I'm sorry. Here is x, correct. Okay, so this line and this is the same qubit, and this is the same qubit. Okay. This is the same qubit, and this is the same qubit. Okay. Okay. So yes, a function needs to be invoked, of course. Other than that, the Deutsch algorithm, the Deutsch construction involves three elements. The first element is the Hadamard gate. The three Hadamard gates, here, here, and here. Okay? The second element is a control qubit set at 1. Okay, it must be set at 1. Okay, and the third element is a measurement. Okay. Usually people use this. Okay. I want to use this, a cartoon for detector. Okay, because like this is the end of the qubit, so I wouldn't mind just drawing that. Okay. All right, so that's the Deutsch construction. This is the minimum. Okay, now first you link them. And this you don't mind, you just disregard. It can be there.
Should it that what we should measure?
No.
Should it that what
No, you don't need to. This measurement here.
That's always X the input, right?
Yeah. These are just the 2 ports. Okay. Yeah. So your input can be any state.
Yes. Whatever the X comes, that will be the output of the first equation.
Yeah. So the Deutsch algorithm is this. Here,
because the properties of F will be on the lower one.
Give me a second. So you measure the first qubit, okay? What you're interested in is the global property of F, of X, right? That's the problem we had.
In the first line, there is no property, right? Because F is not applied on that line.
No, it doesn't matter. It doesn't matter. The construction is a recipe that solves this problem. So you don't need to worry about how he constructs this. What you need to see is you need to verify that this indeed solves this problem, okay, which we will do in a minute, okay? But let me first explain. So the construction is to find out if this is real, if this is constant or balanced, okay? And the answer can be read from the detection of the first qubit. So this is the initial state, okay? And this is after the first Hadamard gate, okay? And this is after the second, right? And this is the final, the outcome, right? Okay. In the final, in the outcome state.
A plus 1 as psi, A tensor product.
Yeah. Yeah.
Okay.
Yes, of course. Yeah. This is a 2 qubit.
Okay.
I'm talking about the system
quantum.
Yeah, the system quantum state.
In the way you draw, it was like only the last line. No, okay.
All right.
Clear.
All right. Maybe this will help. So just going across. Okay. All right. So here you also have 2 qubits, right? Yeah. Okay. What you need to do is you need to inquire. Okay. You need to inquire only the first one. Okay. And if the first one shows no change, unchanged. Okay. Let me erase this. If the first qubit is unchanged, that means it is still the same as what we had before. Then this means constant mapping. Okay, that means f of x is constant mapping. Or maybe I should say f of x constant mapping. Okay, that's what it means. Yeah. So this is like green line, and the other one is of course red line. So changed. So I use a bar, an overhead bar, to represent the inverse. So if you have 1, then this is 0. And if you have 0, this is 1. Okay, so if it's changed, and it can only change between 0 and 1, right? So using the bar to represent the other state. If this is changed, flipped, then f of x is balanced mapping. Okay, so it's like you have a light bulb, a green light bulb, and a red light bulb. And once you run the thing through this machine, if you see the green light bulb turns on, then it means the diagnosis is the function is a constant mapping. If you see the red light bulb turns on, so something has changed, then the conclusion, the diagnosis is f of x is balanced mapping. Okay, so that's how it works. Okay, and in order to really see how this works, we need to use an example. Okay, I think the best way to learn about all this algorithm is to work on examples. A general mathematical proof for us is unnecessary because we are not in the business of creating new algorithms. Okay, we're more of in the business of using algorithm that people create, people have come up with, people invented. All right, so our job, the minimum things that we need to do is just to verify it. Okay, and to verify it, it will be helpful to start with just a particular example. Okay, and once we have that particular example worked out, then it will be easier to see if we can do better and have come up with a general, a more like a faster way instead of exhausting all the basis states, all the inputs. We can see if we can come up with a better way to verify that this indeed works. Okay, let me demonstrate that with two examples. So suppose we have 0, 1. So a as 0. Okay, so suppose we have a as 0. Then this will give us the state as 0, 1 to start with. Okay, so this is the first qubit. This is the second qubit. So let me just write first, and this is second. Yeah. First. Okay. Now, after the first Hadamard gate, so let me write, because it is the first Hadamard gate on the first and Hadamard gate on the second. Let me just write Hadamard gate first and Hadamard gate second. Okay. To show that this. Okay. So Hadamard gate. Now, we know. Huh? Oh, side 2. Thank you. We know how Hadamard gate works, right? Hadamard gate map. Hadamard gate is this.
0 plus 1.
Okay. So if we have 0, which is, so 0 is this, right? This is our basis for 0. That will give us a symmetric superposition. And 1 will give us an antisymmetric superposition, right? So this means we have a symmetric one for this. So now, right now, I will forego the subscripts for the sake of saving time and simplicity of our notation. But it should be acknowledged that the first qubit is the qubit in the front is the first one. The qubit in the back is the second qubit. Okay. So the first one gives us a symmetric superposition, and the second one gives us an antisymmetric superposition. Yep. Okay. Good. Now, what we do next is we expand it. Why do we want to do that? Okay, by the way, probably we could do. Why do we want to do that? Because the next step is to feed x to of f of x, right? So it'd be good to have just then on individual. So 0, 1. Yeah, maybe it won't hurt too much if I just keep the subscript. We'll see. If it becomes too annoying, I will forgo it. Okay, and this is plus 1. Okay. Yep. Now, next thing is we apply the function, right? And so we apply the function, and how does that work out? That gives us, it takes the first qubit, okay, of the first qubit, it remains the same. Sorry. So we just do, we keep the first qubit. So there's no change here. Okay, but the second qubit is changed, right? The second qubit is changed how? It takes the first qubit value, and then it does this, right? And this, of course, works on both of this. So we can distribute it, and then it is like, it is like this, okay? Yeah, and then here, that's 1, okay? And 0 and
1.
Oh, sorry. Yeah, see, it's really easy to get carry out. Okay, and so this is the same deal.
1.
Oh, thank you very much. You're more awake than me. Gosh. All right. So 1.
0.
Is it?
Yeah. It's the
Oh, right. Yeah, this is the first one.
Yeah.
0. Yeah. Oh, wow. Thank you. Just in my defense, I only sleep 3 hours this morning. Or 2 hours. Okay.
1.
1. Thank you. Yeah.
1.
Yes. Great. I think I should have you do the math instead of me. I'm toasted. pretty much toasted. All right. Okay. Great. Now, we cannot proceed further unless we know what function we actually have, right? So let's just come up with 2 cases. Okay. Case 1. We have the balanced. Sorry, we have the constant. Okay. And let's just say this is equal to 0. Pretty simple. Let's just do it simply. So case 1 will give us omega 3, and we need to replace all of, so this is 0, 0, 2, 0, 1, 2, right? And 1, 0, 0, minus 0, 2. Okay. Okay. Not too hard. We just substitute. All right. Now it comes the fun part. This. How does this work? Of course, we can do the case by case, right? But here I would like to offer you a cheat sheet, which is very, very useful in general, and we will also use it.
In this case, we can take it back
Okay, let me first offer you this. Whatever state is modulus 2 with 0, that's the same state. Okay? So you see what I'm doing here. 1, this is flipped, right? It's pretty easy to prove. How about it with itself? 0. Okay? And this with this flipped version, 1. Okay? So this can be shown just by substitute 8 with 0 and 1, and you can demonstrate this to yourself, right? I did not use a general mathematical proof to come up with this. I just summarized what I have done before already, and I found this just pretty general. Okay, so we see that this will give, so we will just use this, right? This will give us 0.
1.
This will give us 1. So flipped, right? And this will give us 1. This will give us 0, right? Yeah. So,
The same as I1, as I2.
oh yeah. So two, 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 two. Okay. So we now we have 4 terms: 0, 0, 0, 1, 1, 0, and 1, 1. Okay. Now, what we need to do is we need to group the sand. We need to group them together, which will give us 1, 1. Yeah. And this will be 1, 1, and 1. Correct? Okay. All right. So this is, so we're grouping them pretty nicely. That's great. And why do we want to do this grouping instead of let them remain as this? That is because the next step we're going to do is we're going to apply Hadamard on the first qubit. So we just want to group everything on the to the first qubit, and then and see what come out with from it. Okay. And of course you can do this,
Yeah,
but
it's better to also group it above this one, right? We can take the first term out also from this. It's common in the board.
oh, we could.
So it's much simpler to apply the Hadamard.
It is simpler to operate Hadamard if we group it like this.
Yes, I mean, you can also take this out and
operate
like the side 2, we get the same equation back, right? The first one. Side 2.
You mean this?
Above. The equation above, just above that.
With this?
Yeah.
Yeah.
We get that, so it's much similar.
All right. I think we're getting to the same point.
Yeah.
What I try to say is the reason we try to group this is because Hadamard is pretty special. Hadamard on top of this unitary, sorry, not H, just H. On top of unitary, it is also Hermitian, which is pretty straightforward because it is symmetric with respect to the diagonal, and it is real numbers. It has real numbers as its element, right? So it's Hermitian. Okay, and these two together will give you the inverse is equal to itself. Right? Why? Unitary is this. Hermitian is this. Right? So this means, right? So the inverse itself. Okay. What that means is if you apply this twice, you reverse the action. You come back to its original state. Okay. So we know that since it's unitary, it's a one-to-one mapping, and the reverse comes to it. Apply it again, we come back to it. Then we know. So this is these two states, or the symmetric state and the anti-symmetric states, are, like intimately linked to 0 and 1. Okay. So here we have a symmetric state, and here we have a sorry, we have both symmetric, right? So when we apply it Hadamard, then this will give us 0. Let me use blue. Hadamard on 1, right? Then this will give us 0.
There won't be square, right? 1 by root 2 square will
Oh,
not
so there's an additional.
So only one time, because it's the inverse, right?
Oh, right. Yes, 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 yes. So it's this minus 1, right? Thank you. Thank you very much. So this will give us this, the symmetric state, symmetric. And this is also symmetric. Yep.
Last time is 1.
Oh, thank you. See, I told you, I said that you were more awake than me. All right. So together, this is this. Two. Okay. Now, the second qubit. So for the after the last Hadamard gate, the wave function of quantum state of the system is phi4, and the second qubit we don't care about. What we care about is the first one. Okay. Now we compare the first one with our input, which is this. Okay. And see, we see a no change. No change, unchanged, imply it is a constant mapping. And indeed, here we have the case of constant mapping. So everything is verified. Great, awesome. And the next thing left to do is to exhaust all the other 3 cases, which include, so there are case 2, and case 2 is this, right? And there is case 3, which is this, and then this is that, right? Case 4. Okay. Yeah. Now, after you go through the tedious arithmetics for one case, you're kind of tired already. You don't want to do more. And so it kind of is not very motivating for you to continue to do case 2 and 3 and 4 unless you get credits from it, right? All right. So what we're gonna do next is to do this. Like I told you, like I said earlier, I think the best way to learn about the algorithm is always to work with one specific example. And after you work through it, you see how the math works. Then you try to think about if there's a better way to carry out the math so that you can verify the thing faster. Okay, so this is like the level 1 calculation. Now I want to introduce the level 2 calculation. Okay, and this won't be so hard. It will actually, I can just do it here. I can just do it here. So they are oh, okay. So case A. Okay, so instead of specify this to a value and a value, let's just do this. Okay, this is sufficient to represent the constant mapping. Okay, now if we do this, then 3 would be f of 0 to 0. Let me just forgo the bracket, and f of 0 to 1. Okay. F of, so F1 is equal to 0, right? So that's just 0 here, f of 0 here, and this is f of 0. Okay. Okay. All right. Now we want to use the magic that we have here. So if f of 0 is with 0, then that's f of 0 itself, right? So every term here, this is f of 0, and this is f01, right? Sorry, this is not f01 bar, f0 bar, correct, f0 bar. So this gives us f of 0, and this together we can group, right? So that's, yeah. Yeah, let's just group then. That'd be nice. 1, and this is f of 0, 2, right? And this is minus. F0 bar, right? Okay. Okay. Now, f of 0 bar What does f of 0 bar mean?
No, we don't have to care about that, right? Now we have only to apply.
Oh, yeah. Yeah.
On the first step.
Yeah. You're right. Thank you. Thank you so much. Yeah. And the next thing we do is we apply Hadamard gate 1 on the first qubit, right? Whatever this is, we don't care about. And so f of 4, that gives us 0 for this and 0 for this. Huh? Right. Yes, thank you. Minus, so this is 0 for the first qubit, right? And this is also 0 for the first qubit, so we can just group then. Minus f of 0 bar. Yeah? Okay. So we see that here, indeed, that is the same as our input. So that's constant, that's consistent, right? Okay, maybe I'll do case A here. Let's see. I think case A will okay. Let me just take. So this is 7, right? 7. Case B is balanced.
0 equal to f0 bar, f1 bar.
F balance means whatever f0 is, whatever f0 is, f of 1 is the other one. So that means f of 0 is f0 bar, right? So this is balanced. So this is important to recognize this relation. If once we recognize this relation, things gets easier, right? So we come back to here. Okay, and f of 0 remain the same. F of 0 remain the same.
f0 bar.
F0 bar, thank you. 0. F0 bar. Okay, great. Now we have F0 modulus with 1, 0, and 1, which we can find answer here, right? What about the F of 0 bar?
f0 bar and f0.
Yeah, that just, so this is F0, this is just F0 bar. Whatever the value is, we don't care. We don't.
F0. No, last one is f0.
Okay.
Oh,
oh, this is F0?
Yes.
Yeah.
F0 is f0 bar.
Okay, great. Is this what we had?
No, switch. In the last two, the sign switch from that.
Yeah, but is this what we have here? The answer is yes. Yeah, okay. Yeah, okay, great. Yep, thank you. So we do it here. Again, we group the first qubit, 1 here with this, -1. So we group according to the second qubit, right?
No, we should group up according to first qubit, right?
minus, minus. Correct?
Yeah.
Yep. Minus 1. I'll give you this. I'll give you this, right? All right, good. So, I mean, so after the Hadamard gate on the first qubit again, because this is antisymmetric, we see that this will become 1. And this will become 1. Sorry. Bar, right? Thank you. Okay. 1, 1, factored it out. 1. Okay. So indeed, we see the first qubit has been flipped, and from the input, and that correspond to the balance condition. Okay, so it's verified. All right, so that's great. Okay. Now, we have pretty much deal with input of this nature. Oh, sorry, that was 0 and 1, right? We could do even better. We can just put a and 1 as a general one, right? And then carry out the same math that we did here, and then we'll still see that this can prove. We will still see that a and a bar will correspond to the case of constant and balanced mapping. Okay, that's not too difficult to imagine. Okay, but now the question is, how about changing the control qubit to 0? Okay, changing the control qubit to 0. So if I prepare my quantum system in the ground state to start with, and I forget to, excite the control qubit before, so in the initialization for the Deutsch algorithm, I forget to excite it, so it still remains at 0. Will this work? The answer is no, it will not. And if you're interested, you could use the same method we do here. This is rather, so using this this cheat sheet, you can carry out the math pretty easily. Okay, and you can show it to yourself.
It's always constant, always remain unchanged. Everywhere it will be plus, right? Everywhere it will be plus in that case. So it will always remain unchanged, I think.
Yeah, you are right. I think I have it. So I have no. So what I have, so I work out. Oh no, sorry. You're right. It is.
You can just put plus in.
It is always unchanged. It is always unchanged. Actually, I work out all these cases for constant and balance. Okay, and then it will turn out that the output, when you have 0 here, it doesn't matter if the constant or balance, your first qubit will always be unchanged. And the same situation here too. So in other words, if you have this, right, your first qubit will always be unchanged.
It's zero. A0.
Hmm?
If you have A0.
Oh, A0, thank you. A0, your first qubit will always be unchanged, and the second qubit will be whatever it is. Okay? And so this does not distinguish between balance and constant. If you have the control qubit equal to
easily see in this
0.
case just putting plus here.
Okay. All right. So I'm glad that you are doing this much faster in your head than me. All right. So great. All right. So that's so much we want to say about the Deutsch algorithm. Okay. How about the generalization Deutsch Josa? Sorry, Josa. So this is pronounced as like Joe. Okay. So his name is David Deutsch. He's a British physicist, and this name is Richard Josa, and he is also, I think, he's Australian, but I think he works in UK. So he's a mathematician there. I think he works in Oxford and he works in Cambridge. All right. So all right. I don't know if we should do this. Okay, maybe a little bit. Maybe just a little bit. Let's see how far we can go with this. I still want to spend some time here. So, of course, a general proof for n is rather abstract. And one needs to be quite familiar with, so probably you're the person for the job. One needs to be quite familiar with this Boolean calculus. The Boolean is 0 and 1. One needs to be rather familiar with this Boolean calculus in order to get a grasp of what's going on with the general proof. All right, so we won't do that, but rather we will just work out a simple case. So for 2-qubit input, so we will increase the space dimension by 1. So instead of this, so instead of this 0, so this 2-dimensional space, we'll do not 2-dimensional, but like this 2-element space, we'll do this 4-element space. Okay, and so this we'll do Deutsch Josa construction. Okay, and so for us, we want to do this. So this is a 2-qubit state. Okay, and as before, we have a function, right? This is a function. Now, since our input is a 2-qubit state, then of course we have this. Yep. Okay, and I will just call it x1, x2. Okay, and the function, of course, with 2 input, the function is a multivariable function, So it takes 2 input, right? And then you do modulus 2 with y. Okay? And the after the operation, the first and second qubit remain the same. Okay, so this is just a generalization of the of this quantum function from one variable to multivariable. And if you want to add more, you can just do x1, 2, 3, 4, 5, all the way to n. Okay, so pretty straightforward. Now, so in the same spirit as the Deutsch algorithm, we have again three three elements. As you can imagine, we have H, 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 and H, right? And as you can imagine, we will have a detector. So the detector is a 2-qubit detector. So you evaluate the 2-qubit, and our control bit is still 1. Okay? So let's link it. Okay, this we don't care about. Okay, and our input in this case, we just gave A and B, right? Okay. Okay. Let's see if we can work it out. Right now, since we have four elements here, the constant mapping, of course, the constant mapping is of course just whatever we have. Whatever we had, it all goes to the same. It all goes to the same 0 or 1, right? So that's no problem. Okay, but how about balance? There are many different versions of balance, right? One of them is you can have 0, 0 and 1, 0 equal to 0, and 1, 1 and 0, 1 equal to 1. Okay, this is just one version. Of course, you can have 0, 0 and 0, 1 equal to 0, 1, 1 and 1, 0 equal, okay? Okay, yeah. So that's just, like earlier it was simple because you only have two elements in your input, right? So if one is 0, the other must be 1. There's only one possible configuration scenario for the balance mapping. So we have, well, actually no, there are 2 because they can be like the zero input take 0 or and 1 take 1, or 0 take 1 and 0 take, there are 2. But like here we have a lot, many different versions.
You can also have like F0 take 0 and all others take 1, right? That's also option, right?
Say again?
It's not necessarily 2 of them should be same and balance means
right. That's what
same, right?
Yeah, exactly. So it's
not
here.
Like 1.
No.
1 is 0, 3 is 1.
No. Okay. You cannot. Yeah. So it's it need. So here you really see what balance means.
Yeah. Half of them should be
right. Half. It means half. Half. Like you could half vote. Half of the people vote for candidate 1, candidate 0, and have the other half vote for candidate 1. Okay. All right. So we can see this like we just increase this dimension by 1, but the problem becomes increasingly difficult. Yeah. Right. But that's just see if we can work out one example, and just to get a gist of how difficult this is. Okay. All right. So let's start with this. Let's start with this state. So this is one. This is two. Okay. And this is the target. Sorry, the control. Okay. So one and two and three. Okay. And so that's what we start with. And like before, we want to do want to do here 1, 2, 3, and 4. Yep. Okay. And so let's start with this 1, 2, and 3. So this is 1, right? 2. Okay. Symmetric, symmetric, and asymmetric. Three, symmetric, symmetric, and asymmetric. I like to do it this way instead of using the matrix, because here you see the structure. If you use the matrix, they are all in a soup of numbers. That's how I feel. So I like to when I work on individual examples, I like to keep the cat notation. Okay.
So it's hard to apply the F operator and get that state
Hmm?
matrix form.
What? Oh, the F.
Hard to apply the F operator and use the node in matrix.
Oh yeah, right. That's true too. That's true. Yeah. Okay, so let's save us a few steps. Okay, we know this is basically all combinations of the 2-qubit states, right? So, and they're all plus. Okay, so let's just save us some trouble, and then just do this. Okay, and so the 0, 0, 0, 1, and this is 1, 0, 1, 1. Okay. So now I forgot the subscript from now on. Okay, otherwise there's too many numbers to write. Okay. Yep. Good. Now I want to apply my function, right? I apply my function and then give me 3, 5, 3, size 3, and it will take the first number and then couple with this and this. Okay. So it looks like this: 0, 0, F0, 0, F0, 0. See, this is not hard. It's just tedious and it requires a lot of patience. So it'd be nice to have a cup of coffee and some jazz music played, and then just focus on listening to the music while your hands work on work on the work on writing down all the numbers. That's what I would do. Unfortunately, I don't have that luxury anymore. When I was a grad student, I can get coffee, go to the library, and spend the whole afternoon just work on one sheet of calculation, and then just enjoy myself. Right now, I barely have enough time to sleep. So that's how life evolves. Gets worse. All right.
And the last one is one.
Sorry. The last one is one?
The last one.
Oh, thank you.
We can just use the node now, right?
Yeah. Let's do it step by step. So we have 1, 1, 1, 1. Correct. 0. Yes. Okay. So check. Good. Great. All right. This is not working. Very great. Okay. Now, like you said, let's use this cheat sheet. Okay. So we can get rid of the second. F11. Bar. Okay. Thank you. It's great to have
one without bar and right one with bar.
Yeah. So you always repeat this pattern, right?
Yeah.
Mm-hmm. Okay. Yep. Okay. Now, so now it's time to.
Constant map case.
Yeah. We can do constant mapping. Let's see. Okay, we can afford to do these two cases. Okay. It is not too difficult. So case 1, constant mapping. This is the easiest to do, right? So with constant mapping, all of them have the same value.
Left one same, right one opposite.
What do you mean? They all have the same value, right?
No.
Huh?
All the left one will be same value, right one will be the opposite value.
This?
Yeah.
That's the same value.
Yeah.
What do you mean by left and right?
Oh, that and all the 4 terms, that will be same value. And the other one will be opposite value.
Oh, yeah, I see what you mean.
If the first one is 0.
Okay, I see what you mean. Okay, of course, sure. But that's just let's just group them together.
Let's put RF00.
1.0, 1.1. Okay, and all of them are the same. So all of them are the same as this, right?
Yes. Yes.
often are the same, right? Okay. Now, what do we do with this?
You can split it.
Well, we cannot do anything about it right now. But when we apply the next gate, right, we will see that this very, very likely correspond to 0
Yeah, that.
because it's symmetric. Okay? And we have this. Okay? Now, there is a quick way to find out, and this is actually very useful.
You can see here, like in the left.
So this property, this is called a involutory. This property called involutory. So that means you apply it twice and you get back to or the original. This is especially useful when you have multi-qubit state. Okay, let me explain. So when we have this, right, that means we have a product like this, right, and that is 1 0 0 0. Yeah. Yes. And we have this. We have 0 1 0 0, right?
Yes.
Okay. Now, so you can imagine that when we have, we call this, I think we call this, we use this notation. That means 2 of them. We have tensor product for 2 of them. Okay. So if you have n, you do n, but here we have 2. So what you do is you, of course, you do this square, right? Now this tensor product is not too difficult to do. This is basically just going in block, right? So you take the whole thing, you multiply by this number, 1 1 1 minus 1. Whole thing multiplied this by this number, 1 1 1 minus 1, 1 1 1 1 minus 1, right? And then the last one, you have a flip. Okay, so minus 1 1 1. Okay. Okay. Now you can see that when I apply this to 0 state, I get this road, right? Symmetric. All the coefficients are symmetric. But for this, the second one, I get plus minus plus minus. Okay? And of course, as you can imagine, this is the third one, and this is the fourth one. Yeah. So this coefficient that we have here will tell us where, because this is 1 to 1, so which state it comes from. And when we apply this twice, of course, you get back to its original state. So this will correspond to this state. Okay? All right. So this is going to be useful when we discuss the balance case. Okay. Where is my pen? There. All right. So that's try the balance case. So case 2. Balanced mapping. And and here we have 0, 0 equal to 1, 1, the 0, and 0, 1 equal to. Did I give this example earlier? Anyway, it doesn't matter. Okay, it's 1, 1. Okay, just one thing. Okay, and from here, you can summarize that the inverse of this is. You can do this, right? For this specific case, for this type of balance mapping, right? For other type, you have a different relation. But here, this is what you can use in your calculation, right? So when we have this,
no, step below.
Oh.
You can directly use from there. Yeah, this
Right. Thank you. Yeah, thank you. So thank you very much. So we can start with this. Let me just write here. Here, this is star. Okay. So star. We go from star to. Now, we evaluate all this. So this gives us
0, 1. You can directly use that, right? We have 0, 1 defined already, so you can use that. Instead of writing it above it.
True. But we could also, what we could also do is just, because we also have the possibility of this equal to 1 and 0, right?
Yes.
So we could just say, okay, this is one value. This is one value, and this is another value, and they are not equal.
Yeah.
Okay, and this will be a little more general, just a little more. Okay, and so this gives us this. The first state stays the same. The second
flips.
The second one is flipped.
Third also flipped. Fourth, same.
One, yeah. So this is the same as this. Okay. Yep. So now I have everything written in F00 or F00 bar. So I group them according to FF0 and FF0 bar, and actually no.
So second and
that they are just like a minus sign different. Yeah. So this is very convenient. So we can just put 0, 0, minus sign, and this is minus sign,
plus.
And this is plus, correct? Okay, and yeah, all right, great. This is awesome because we immediately see that the dot
spot 1
will give us. So here we have +1 minus 1 plus 1, right? Yes. +1 minus 1 minus 1 plus 1. This is this, right? And this comes from this guy. Okay. 1, 1. Okay. So we apply this again. We get back to 1, 1. So that's where that comes very handy. Okay. 1, 1. If you try to apply this to individual bit, oh man, that's just a lot of work. Okay, but here, fortunately, we have the tensor product to our disposal. Okay, great. So this is what we have, right? Now, we started with 0, 0, right? And we see that 0, 0 is now flipped.
Both are flipped.
Both are flipped. So, and this indicate a balanced. Okay, so BAB, if AB does not flip, okay, so AB, let me just write 1, 2, and 1, 3. And if they do not flip, so it's just a summary. If they do not flip, okay, whatever this state is, if they do not flip, this means constant mapping. And if they do flip, and they should flip in the way that both qubits are flipped. And this is balanced.
From the example, like all balance, I don't think in this case all balance, both of them will be flipped. Only in the particular use case, both of them will be.
So
at least one will
so
be
if I
flipped,
have, for example, 0, 0 equal to 0, 1,
yeah,
and 1, 1 equal to 1, 0,
then I think you will get another coefficient, which is like,
okay, you're right.
so
You're right.
it's like
Yeah.
at least one.
I will probably have
Yeah,
this one or this one,
yeah,
right?
Exactly.
And then that is only one of them flipped.
Yes.
Okay, so you're right. Thank you. So one of them flip. I don't know how to represent that.
Or not equal to that.
Huh?
You can write it is not equal to AB.
Oh, okay. So just, I don't know how to, like, not.
In the arrow mark, you can put not equal to.
How do you say not equal?
You're putting the arrow mark, right? Left side arrow mark, right side, right? So this.
I don't see it.
Okay. See here.
Get out of here. Okay, so anything
other than this,
other than that will indicate balance mapping. Okay, so that's the general rule. So like, okay, we have not exhausted all the possibilities, but see, after working with one specific example, we see the machinery, and we can immediately see that, oh, so the balance condition is, like you said, if this is not equal to exactly the same, then it is balanced. It doesn't matter if one flip or two both flip. Okay, so that's the advantage of working with one example. You have like a very concrete idea of how this works, and what's the message behind it. How does it, the operational definition of it. Okay, so I think that is great. All right, so this is 10. Okay. Should we do a little break? You good? Okay. All right. We will race to the end. Next week, we will do, so this is actually 2 lectures worth of material. Yeah, because I am hoping to save the last lecture for polarization entanglement, because we're going to do that too as one of the bonus lab. So we're going to have the Deutsche algorithm and on one table, and the polarization entanglement on the other table. So I'm hoping I could use, because last semester we didn't have that. We didn't have the polarization entanglement set up as a bonus lab. So so I did not give a lecture on polarization entanglement, and that has to do with the John Bell's inequality. So I will try to explain that next week. Explain both the concept and the optical implementation of it. So that's why I'm like squeezing 2 lectures in one. So this lecture again will be unusually long, but let's see if we can rush through it, since you are pretty fast in catching up, and I don't know, I don't need to use many words. All right. So
is the optics 7th lab setup all right? No.
no, the whole Mandal. No,
No, not Homental, the other one, 7th one, last with the stage.
I don't. You mean the? Oh, you mean the automatic scan?
Delay choice numerizer.
Yeah, yeah. The only thing with that one is you cannot do an automatic scan. But I think that's fine. You're oh, maybe not fine. I think it's fine because you're only looking to see whether you have oscillation and no oscillation. In the previous one, you need to like measure the envelope, and so the to getting like the good oscillation is actually important for you. But in this lab, you just need to see if there's oscillation at all or no oscillation, depending on your measurement scheme. Okay, so all right, maybe I will start with 11 and this 12. Okay. So the optical implementation. I will first define. So to do the Deutsch algorithm, we need to have 2-qubit input, right? A 2-qubit state.
One thing I didn't understand in the Dodge-Josha case that we draw is the output we still had 2 qubits, right?
Yeah.
For state either 0, 0, 0, 1. So it is. I don't understand why we have like 0, 1 set n goes to 0, 1 set, because number of
this
is equal to number.
No, this equal to that, or you see?
Okay.
This is what it means. Your output.
Okay.
Your output is limited to 0 or 1. Okay. There are no other numbers. So these are the output value the function can take. Yeah. Okay.
Yeah. Not every.
Yeah. Yeah. If it has more numbers, then you cannot. It's like difficult to define balanced. Okay. But see, this is not a very useful. This is like not a very practical thing, but this does demonstrate quantum advantage. And so this means when you have built a quantum computer and you want to test it, right? So instead of trying to figure out a way to demonstrate that your quantum computer is indeed better and have improved performance, you can just run this algorithm and see how much time it takes for you. And you can have the classical computer do the same task. This is really for benchmarking purpose. Okay. All right. So so for the Deutsch algorithm, optical implementation, we need to have a few things straightened out first. Okay. In the Deutsch construction, we have this. So just like a simple schematic of what is involved. Yeah. We have 2-qubit. Okay, so first we need to have a 2-qubit state as input. Two qubit state. Okay. Now the 2-qubit state can have the same nature, or they can have different nature. Okay. For example, they can both be, for example, the atomic level, or polarization, or something, some degree of freedom that have the same nature. And if they have the same nature, then the gate will have the same nature. Okay. But if the 2-qubit have different nature, so if you don't have two physical elements, so to have the same feature, if the 2-qubit have the same feature, then you must have, it probably it almost imply that you need to have two physically distinguishable systems, and one take a certain state of, like atomic state, and the other also take atomic state, but right. But if you don't have two particles, you have only one particle, you can still do you can still have 2-qubit state. You just need to use different degree of freedom as their quantum state. Okay. So in that case, you need to have different gate, Hadamard gate, for different degree of freedom. Okay. Gate for qubit 1, gate for qubit 2. Okay. 3 is measurement, right? Measurement, like I said, if you have only one particle and the 2-qubit state correspond to 2 degree of freedom, then measurement 1 is the measurement for a specific degree of freedom. Okay. So measurement for qubit 1, and it doesn't matter if you cannot measure the second qubit. It's just it's immaterial. It doesn't. If you can measure the second qubit or not, if you have the capacity to measure the second qubit or not, it's immaterial. Okay. You just need to make sure you can measure the first qubit or the first degree of freedom. Okay. So for optical implementation, what will be our 2-qubit? What will characterize our 2-qubit state? We will have the first one as path qubit. Okay. And this is it's kind of silly to call it path qubit because path is not quantized. Okay, but nevertheless, we could define, horizontal as one path and vertical as the other path. So and the two qubit states are orthogonal.
So it's like polarization.
No, it's the traveling direction. Okay, so we define this as 0. No, sorry, this as 1. So horizontal path as 1, vertical path as 0. Okay? Or you can call it momentum. But we use this.
I don't understand how would it means if we have this as our dictator or something.
It's rather an artificial construction.
Okay.
It's not really quantum. We are just trying to illustrate. So rather than say, so in my opinion, all the photonic realizations of quantum circuits, they are not really quantum, they are classical. And they are just at most like a simulator for a quantum circuit. Okay? Because the quantum coherence of photon or the quantum coherence of the field is not used. Oh, maybe you can say yes, entanglement does. So unless you're dealing with like entanglement, then yes, you using the quantum nature of the photon field. But if you're not, if entanglement is not involved, then I would just say it's like a classical simulator of a quantum machine. Okay, the purpose of that is to just to show you how to give you like a physical layout of your abstract algorithm, but it is not really for the purpose of demonstrating the quantum algorithm. You see what I'm saying? So the optical implementation.
But we have some of the like HOM kind of circuits also we can build, right?
Say again?
Home HOM.
Yeah, home and down.
Circuit we can build, which also use the quantum method, right?
See the Hong-Mandel interference has to do with also entanglement, right?
Yes, yes.
Yeah,
because the
yeah,
because
yeah.
both squeeze
Yeah, and it strictly has to deal with Fock state. Okay, so there the element like the elements of quantum light is in it.
Yes, and also we are producing two lights which are entangled there.
Right.
Which we are
So there the element of quantum light is in it, but for a lot of things that we do in in photonics quantum computers, I would say we are not using the quantum resource. We're using the interference, we're using the polarization, and those are all classical properties. You see? But still, we can manage to cast this into a language of, like for example, the Hadamard gate is halfway plate rotation and that kind of stuff. So I would say this is more like a classical analog. It's really like a classical analog of a quantum machine. It does not demonstrate the quantum uh, superiority or quantum advantage. It does not use any quantum property in it. And of course, you can have superposition in light. That's no problem. But that doesn't come. That superposition does not come from its quantum property. Okay. So, and of course, superposition is a quantum property for matters. So we are really using like a classical superposition to represent the quantum superposition and then just to simulate how this work. So it's more like a little illustration than demonstration. Okay, so I want you to keep that in mind because otherwise you'll be confused. Like, what is quantum about this? Because as you see, the same algorithm you can run with single photon light source. You can run with the alignment, the coherent light source, the laser light source. It doesn't matter what light source you use. The algorithm will just work, right? So it does not really require any quantumness in your light to do it, right? So at most, this is really just like a classical illustration of the quantum algorithm, yeah, not a demonstration. If you're using trapped ions or using MV centers you're using neutral atoms or superconducting qubits or semiconductor charge qubit, and you do this. Yes, that's a demonstration of the quantum algorithm. But here, what we do with the optical implementation, since we're not using entanglement uh, or Fock state, right? Like or any like non-classical state, then we'll really just at most
Normally we'll be using
a classical illustration. This is at most a classical illustration of quantum algorithm. Okay? Yeah? So just have that in mind, then you won't be bothered too much with, like what's quantum about path? Okay, what's quantum about polarization? Okay, so they are just classical properties. Okay, so anyway, so the first we call it path qubit, and the second one we call it polarization qubit. And this is not really a quantum bit, right? But this is just a binary state, but anyway, we just use it to represent qubit. Okay, and
so you're saying with single light source, we are within one light, we are taking it as path and polarization in the same one?
mm-hmm. Yeah, you just take a single beam, a single laser beam, and if it goes this way, it's represent state 1. If it goes this way, it represents state 0. And it represent, yeah. So, right. So I'm gonna define it here. The polarization. This is called H, horizontal, right? And horizontal is represent 1. State 1 is assigned to state 1, and vertical is assigned to state 0. Okay, so that's first to get our language straight. The 2 qubit state for I won't say photon, for the light, because you see, I think there's a lot of misusage of the word photon, so I kind of refrain to say it. Okay, but the 2 qubit state of light in this case will be the discrete path state plus the discrete polarization state. Okay, so that's this first thing. And now, so this is our qubit gate. This is gate. This is qubit 1. This is qubit 2. Therefore, the gate, the Hadamard gate for path is definitely different from the Hadamard gate for polarization, right? So we'll discuss this in a minute. Okay, and of course the measurement of qubit 1, right? So a measurement of qubit 1 is just pretty simple. You just put either detector here or detector here. Measurement for qubit 2 will involve polarizers, right? Which we don't need because we are only detecting qubit 1. Okay, so that's just for that just to get our language straight. Now, so here we need a little bit of explanations. So this is H gate. For H gate, sorry.
Isn't H gate just a beam splitter?
Well, let's find out. That's a good question. Let's find out.
Gate for polarization.
Let's do the polarization first because that's easier. Okay. So if you want to have a gate for polarization, then you need to have rotations. You need to be able to rotate your polarizer. You need to have unitary rotation. That means you cannot reduce its intensity, right? So for example, from V to H, right? If I use a polarizer, then that wouldn't work because yeah, I can do this, but then that will kill my intensities, right? So that's not unitary, right? Unitary means the probability is conserved. So what I need to use is phase retarder. Phase retarders or comes in two. Uh, in general, it comes in two flavors: the half-wave play and the quarter-wave play. Okay, and what we're gonna use here is the half-wave play, and this is how half-wave play works. If you have your E field input E field in this direction, right? And it is making an angle with the optic axis of the half-wave play. By the way, the optic axis of the half-wave play is the phase axis, which is also the extraordinary. Is the extraordinary axis for in birefringent material. Okay, so basically any birefringent material can be used as a phase retarder. Okay. Now the the uh, half-wave play retarder means when you have an angle, when your polarization have an angle theta with the optical axis, your output will be pulled towards the from your original position polarization towards the optical axis and over by theta. So you have a 2 theta change in your output field. Okay? So therefore, if this is vertical, right? If E in is vertical polarization and you want E out to be horizontal, what is the angle you need to set? 45 degree, correct? Okay. So that's that. And this is what we call an X gate, right? Because you just have a flip from 0 to 1, right? From 0 to 1. So this is X gate. Yeah. How about if we do this? How about this? So that means if this is H, this is V, okay, I'm using vector, then this is that, right? So if I want to rotate this to here, yeah. Okay, great. Now, what about if I start with this? I mean, this is pretty obvious. If you start with H, right? If 45 degree, the same thing will rotate you to V. Yeah, that's no problem. You won't have like a. So by the way, we're not talking about. So this is kind of wrong. This is misleading. So because here we are talking about we also care about phase, right? So so this we define as this polarization in this direction. This will be minus h, okay? And this is polarization in this direction, okay? All right. So I put the arrow at the end to indicate this is polarization, and I put the arrow in the middle to indicate this is path. Okay. Now, so V to H, this you have population transfer. You don't have a phase, a flip. Great. So that's 45 degree. How about H to V?
Minus 45.
H to V, H is here.
Yeah, if the optical axis is above,
So
then
this
it's
is
minus angle, right?
so this is actually, if you call this, okay, let me get my, let me be more rigorous. Okay, this is from here to here. Okay. Yeah. So this is minus. Okay. Because this is clockwise rotation. This is minus 25. Okay. So if I have h here, right? Then I need to have this as plus 45 degree, right? And this will be pulled towards the optical axis and then go there. Okay. All right. So this is X gate. All right. How about this, as we said? Okay. And then you said, my target is here, so this is just simply minus 25.5. Yeah. Mm-hmm. Yep. Okay. How about this? If I do this here, then this, if I do it here, then this will be that too, right?
Yes.
Okay.
But
But this is not what we want, right? What we want is we want, because our purpose is to get, so we try to get Hadamard gate, right? Okay, so this is 0, 0 is symmetric, right? And this is 1, 1 is antisymmetric. So we really want, what we really want is this, right? We really want is the antisymmetric one. And this is 0, and this is 1. Yeah, one antisymmetric one. So this is here, right? So what we need to do, what do we need to do? You see, this is pretty far away from here, right? Can I do this? No.
no, it'll be minus.
I will have to do this, right? So what is the angular difference? So it's 45 times 9 plus 90, right? 45 plus 90 is 135.
That's the total angle.
Uh-huh.
Divided by 2.
Yes. So this is, and I need to have plus rotation. So this is plus 135 divided by 2. So this is plus 65. 67.5. Okay. Okay, great. So this is what I want. Yeah. So this guy, yeah, this guy and this guy. This is my Hadamard gate. See, it's not just have a wave play there give you Hadamard gate. You need to go with specific angles. Even if you have like a symmetrical rotation, it won't work. Okay, you need to have like this.
But for Z gate, we can always put theta equal to 90 degrees, right?
Z.
Yes.
You're talking about a pi phase shift
Yes.
here. How do we do a Z gate? Oh yeah, we just do like 90 degree. Yeah, we just do a 90 degree. Yeah, whichever direction.
Only for H. For V0, it remains unchanged, right?
No, the angle is with respect. This is not the absolute angle. This is with respect to the original polarization, right? So this is original polarization. So minus means counterclockwise.
Yes, I mean like for for Z gate
clockwise.
And
this is
if we have zero state, it remains unchanged, right? How do you do that? Theta equal to 0.
So if you start with this state, V, right? Then you need to put your, you can do either minus 90, okay? Or you can do plus 90.
No, we should remain unchanged in Z.
Oh.
0 degree, right?
Right. 0 degree. So, right. 0 degree unchanged. And H should be flipped. So, okay, so you can do plus 90 or minus 90. Both will give you flip, right? So yeah. So basically, you just need to set your optical axis in the vertical direction, and that will give you a Z gate, right? Because that doesn't work. That doesn't have any effect on V. Yeah. So plus minus 90 will give you Z gate, which is this, right? No. This is a Hadamard gate.
Yes.
Okay. So this is working for B and H. All right.
For V it's 0.
Huh?
For V, angle is 0.
No, it remains
Same,
yeah.
So theta should be 0.
No. Okay, sure. But in terms of the absolute position, it is just vertical. In terms of the absolute position, it is vertical, right? Okay. Let's see. Yeah, but see, this is $69. Okay, so in terms of so let me just use this indicated absolute position. Okay, in terms of absolute position, this is 0. This is a Z gate. Okay, We use phi to represent it. So theta is the relative position, relative rotation, and this is the absolute position. Okay, so you set this here. I'm sorry, you set this here. So the absolute position will x. Okay. So this is optical axis. Optic axis. This is y. So in terms of absolute angle, it is 90. And 90 gives you the Z gauge. How about H? In terms of absolute position, it is 60.5. It is here. This position, 60.5, is minus 22.5 from the vertical. Okay? Yeah. So if I have a table, right, then I can set this at 60.5, and this will work for V and H, right? How about X gate?
45.
Yeah, the absolute position is 45. Okay, great. So we have figured out a few gates for the polarization qubit. Now, for the for the path
HK2 is like
what?
HK2 you written.
Yeah.
HK for qubit 2 is H equal this one with H equal to 67, right?
Right. Yep. Yeah. So yeah, if you want, I could put H2 here.
And also inside the F, we have to define one of
Let
these
me first do a notation here. So this is our 0. Sorry, this is our 1, right? This is our 0. This is for the path. And this is for polarization. Polarization is H. H is our 1. Then V is our. Okay, so these are just notations. We can assign this as 0, this as 1, but our matrix representation will need to change accordingly. So as long as you are consistent, it's fine. Right. So the the thing about path qubit, this is a little, it could be a little tricky. All right, so first, if this is 1 and this is 0, then this is the superposition, right? Yep. But this does not represent a vector. This is just represent, unlike polarization, this does not represent a vector. This would just represent the portion. Okay. Okay. So how do we have a superposition of both for the light to go both this way and this way?
That is this.
Hmm?
You need polarization or path?
Sorry, path. How do we make it to go both this way and that way?
We can put a beam splitter
Yeah. Yeah,
Yeah.
because it's
Yeah,
a
we
wave.
have this.
Yeah, it's a wave. So it can naturally be split. Okay. So a beam splitter looks like this. Yeah.
No, we don't have three. It'll be input, right? For the below.
Oh, sorry. A beam splitter
This.
looks like this. Okay. So it has this vertical in, and it has this horizontal in, right? And and remember how we deal with the transformation imposed by beam splitter. So we have, for example,
Use the imaginary matrix.
a1 in and a sorry a1 in and a0, right? A1 in, sorry, a0 represent the vertical in, and a1 represent the horizontal in. Okay, and we have the a3 represent the horizontal out, and a2 represent the vertical out. Okay, vertical in, and this is vertical out,
Horizontal out.
a horizontal out, and this is a vertical out. Okay, and remember there are. So I sent a note through email. So remember when we were talking about the quantum operator transformation of beam splitter, I used the symmetric construction. So with pi over 2 phase on both reflecting sides, right? So that will correspond to uh, A2 is equal to uh, I,
zero plus
A, sorry, let me just start with 0, 0, and I1, right? And A3,
A0 minus I minus I.
no, A, no, there's no minus, it's just
Oh, IA0
IA0 plus A,
A2 A1.
A1, okay? So this is the symmetric construction, okay? So this will work, all right? But you're right. Then you say what about the asymmetrical construction? Can it work? And I sent a note showing that actually the asymmetrical construction is the more natural one. It has like the physical process corresponding to it, relating to the. It's not necessarily the imaginary number, but it's really the internal reflections and like you need to go into the detail of what happened at the interface in the index of reflection from high index of refraction material to low index of refraction material and how the phase changes. If you track that, then indeed you get what you get is a symmetrical, asymmetrical construction. I think it looks like this. Uh, Okay, so this is like a conceptually more convenient because it's symmetrical. So like all your math are pretty symmetrical, but this is a more physical uh, choice. This is more physical. Okay, So let's go with this. Okay. And yep. And of course, this is just A2, A3. A0, A1. Okay. All right, now we want to just give it a little different notations. All right, let's call this C. The horizontal in, let's call it C. Okay, and the vertical in, let's call it D. Okay, and this is called A, horizontal out A, and vertical out as B. Yep. So here our notation becomes B, A, so we just replace A2, A3, okay? BC, yeah? I wonder if, oh, the, in, by the way, in the physical notation, the dagger, so the raising operator and lowering operator have the same relationship, okay? So because for our purpose, we want to represent that we are creating the state in this direction. So we really, so AP, and so this is really, this is, you know, what we really mean here. B is this. What we really mean is this, okay? And but of course, this is equal to, this is just the conjugate of that, and then you flip everything, and then this is A0 dagger, A1 dagger, and that is our C and D. Okay, so maybe let me just be more specific. Otherwise, there could be confusion. Okay, so I'm using A, B, and C to represent the dagger. Okay, creation operators. All right. So your question earlier is, oh, is the bin splitter a Hadamard gate? You see, our input. So this represent our two input state, right? This is 0. This is 1, right? 0, 1, right? So this is all consistent. And under this definition, the ground state here, 0 here, 1 here, you see that the matrix, the transformation of the bin splitter does not have the form of a Hadamard gate. Why? Because the Hadamard gate have the minus here at the diagonal turns, at the second diagonal turns, not of the diagonal turn. All right. So in order to fix this, we need to add something in addition. Okay. And that is mirror. Mirror. Yeah. Right. Right. That's that just for now. Let's just stick with the conceptual construction. Okay, so let's say we need is a phase gate, a Z gate actually. A Z gate which is also a pi phase shift gate. So if we have this, then and we can have Hadamard. Okay, so you can just, so this is just, you just construct this by trying arrows, and then you see that the phase gate would do the job. Pi phase gate would do the job. Okay. Yeah. So 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 this is a beam splitter. So this is beam splitter followed by a pi phase shift. Okay, and this together is a Hadamard. Okay. Yeah, so that's the conclusion. The Hadamard gate is a phase gate, a beam splitter followed by a phase gate, or Z gate. Okay.
But in this case,
And you're thinking about, okay, how do I realize a phase gate?
in path terms, right?
Huh?
In terms of polarization, we know. In
Yeah.
terms of path, it's just a reflector, right? Yeah, just reflect to the opposite direction.
Yeah.
So we can use two mirrors, right?
Oh, yeah, that's a good idea. Right. Yeah, that's a good idea. Use two mirrors to. So not, if you use one mirror, it will follow the original path. But you use two mirrors, then you will flip its direction, but offset from the original path. Okay, so that's great. Okay, so I think we're ready to talk about.
And also we only need to put that in the direction of horizontal. Vertical, we don't need to put it.
Sorry?
We only need to
Right.
put it on horizontal out. Vertical out, we don't need to put
Right, right, correct. Yeah, because this is only acting on the Z gate is only acting on the horizontal. Okay, so this is 14. All right, so now we are ready to build our
function.
Our optical implementation. And this is going to be pretty straightforward. So that's, again, draw our beloved diagram for the Deutsch algorithm. Okay. Yeah. Okay. Now, for us, we have only one. We're using the 2 degrees of freedom of one single laser beam to represent the 2-qubit state, right? So what we have is something like this with the polarization, okay? So when we start with, what we have is, so we can start with horizontal polarization, which in this case will be like out of the board. I cannot do this. The polarization is perpendicular to the direction of travel. So here I have C and H as my, let me see. Okay, let me just use this. So this is my input state. Okay, so that represents A and 1, right? H is, yeah, 1 is H. Okay, so this is A1.
So first we need to use a polarizer to make it to the only allow horizontal path.
Sure. Yes. Yes. Correct. Thank you. Or if you know your initial polarization.
We are just starting from the laser, then you.
If you start from the laser and you use a polarizer to measure which polarization it has, yes, right? Then you can replace the polarizer with
yeah, that's
with the halfway play and rotate it to your desired position, right? Without losing your intensity. Okay, so this you can do. Okay, now this is your initial state. Okay, and the first thing we're gonna do is we're gonna do a polarization Hadamard, right? So a polarization Hadamard is a halfway play at 60-75 degree absolute position. Yeah, and then so that flip that is this. So this is H2. Okay, let me maybe use a different color. So this is A1, and this is H2, right? Of course, I want to 1 and 2. 1 and 2, okay? And so this is H2. How about H1? A beam splitter, right? A beam splitter followed by pi, okay? And it should work on the pi should work on the horizontal only. So it is really this, okay? Okay, so this is a Hadamard gate.
Also, there should be a remark up, right?
Huh?
There should be a remark going up also, right? If you are using optical. Beam splitter should have two outputs, right?
Oh, hold on. Um, the beam splitter has two outputs. That is correct. But that's that's
Let's continue.
that's because you see when you go here, right? The vertical does not go through a pi over 2. Yeah. So it's not a Hadamard for.
No, it's hard. Vertical doesn't need to go to pi over 2 to have a hard map. Let's look at that after finishing.
Oh, right. You're right. Yeah. So this construction is really this.
Yes.
Right, because yeah, the vertical doesn't go. So it's really like this.
But there is no input from the down, right?
Yeah, it's fine. Okay, I get what you mean. Yes, you're right. Correct. All right, cool. Good. Thank you. So after that, we have the function. Okay? And this is, by the way, this is path A, and this is path B, right? According to our notation, path A and path B. Okay. And here we will do function, okay? And the function is, how does the function work? So this is x, this is y, and this is fx, y, and this is x, this is x. Okay. So how does this work? The function means if I have something in, if I take path 1, sorry, yeah, this is 1, right? So if I take path 1, then something is going to uh, flip. So I am starting with 1, right? Okay. So this something is going to work on my polarization, okay? And if, for example, if we have this, right? Then the effect is that it does not change my polarization.
Yeah.
Okay? But if we have this, then the effect is it will flip my polarization. Okay, so what does this mean? Okay, so if we choose this function, okay, if we choose this function, we're not talking about balance or constant yet. So we're just talking about like which value should this one take, okay? So if we make our choice that when we take a value here, the function, it will always impose a flipping action, okay? So you flip from horizontal polarization to vertical. So what does that correspond to?
Escape.
That's escape. Escape polarization is HO.
45-degree.
Yep.
SW.
Yeah. So 45-degree. Okay. So this is this choice. If we take this choice, if we take the other choice,
0.
then we just don't put anything there. Okay. That's less interesting. So let's take this choice. Okay. So that's that.
Does inputter change that to 0?
Hmm?
You can change that to 0 or 45.
Sure. Sure. Yeah. If it's 0, then it has no effect, right? But okay, sure. Yeah. But let's stick with this. And say we want to have, if we stick with the choice, then if we say we want to have a constant function, right? Then the other one that takes path 0 will also do the flipping. So we need to put right? So that's a constant function. If we do a balance function,
only put one place.
right? Yeah. Or, like you said, we could put here 0. That will give us a balance function too, right? Absence or set it at 0. Okay. All right. I like this version better. Okay. So
we can just change the angle and get all the different measurements.
right. Yeah. So right. So you can put like 0, 0, then all of them is constant function. 45, 45. That's constant function. 0, 45 or 0, 45.
Balanced.
That's balanced, right? So you can have all combinations if you just play with the angles. Okay, great. So that's this, right? And lastly, we want the first qubit, the path, to go through a Hadamard,
Another beam splitter.
another beam splitter, correct?
So,
all right. So
we need to use 2 mirrors, 2.2, I think 4 mirrors would be better, right?
so how do we do this?
You can put 4 mirrors, right? One here, then
If we just have 2 mirrors, okay? If we just have 2 mirrors, one here, one here,
then we will switch the paths.
Yeah, that's like the X gate.
Yeah.
Okay. So that would be like an X gate before the Hadama, right? And that probably won't work.
If I think XHX is Z. So we can put a Z there, right? A Z. Oh, we can put like this, right? So we have like this. So this
Mhm.
is here. Meter here.
Okay, what is this?
This is
So,
the two
so,
mirrors you
this,
put.
so this is the two.
This is the starting point. This
Okay.
is the tube mirror you put.
Yeah. That's a good idea. Thank you. So, in principle, I will need two beam splitters, right? If I have two beam splitters, so without a mirror, if I just have two beam splitter, would that work?
Yes, then we need 4 detectors.
Yeah, but that will work.
Yeah, that
right?
will work.
Okay, so the really dumb, the poor man's intellectually poor. The poor man's construction will be, I put another Hadama gate here, okay, and I put another Hadama gate here. Right? That would do this. Okay? And then after that, I have how many output ports? 1, 2, 3, 4, right? I need to put 4 detectors in order to examine whether I'm going this way, right? Whether I go this way as 0 or this way as 1. Yeah? All right. So that's rather cubism. And your brilliant idea is that we can sort of fold this into one if we just add 4 mirrors. Okay, and 4 mirrors are definitely cheaper than 4 detectors. Okay. Actually, we still need yeah. Actually, you know what? We need what we need is minimally 2 detectors. So we could do this. Okay, but still 2 detectors. The price of 2 detectors is more expensive than the price of 4 mirrors plus 1 detector. Okay. So what you're suggesting, which I in hardly agreement with, is this is not working out very well. Let me use orange. So we could put here a mirror, here a mirror, like you said, put it here, put it here. Okay, but if we put a beam splitter here, then that will be X gate in front of
Yeah, but
the Hadama.
in that way we can do another thing. It's like Z H Z is no.
So we just apply 2X gate because 2X gate also give you I, right? So that's the idea here. So to put 2X gate here and here. So this will mean, so this bring them back together. And here you put a beam splitter. Okay. And then here you only, of course, you have 2 ports, but you only need to detect 1. You only need to detect 1, right? And to see if there is intensity or not. So in principle, it is either it doesn't require a single photon to work. All the phases, the destructive and constructive interference will dictate that all the light power goes here or there. Okay, and if you have it go here, right, that means it's same as original, it's unchanged, and that will mean a balanced. So that means balance means this is different from that. Okay, and if you put this at the same setting, then this will go there because it will be changed. Okay, so this will be the optical implementation of it, and I won't bother to go through the math again. I think this is pretty straightforward.
Yeah, math is same as what we did.
Yeah. So I won't bother to do that again. Okay, so after we have worked carefully on each element, all the math will carry out the same way as we had before. So this is optical implementation. Okay. All right. Now, I want to say that this.
Is there any problem when you put it like that? There is a junction where it
No.
goes,
This is no problem. Yeah, this is the physical skin.
Yeah, I mean, like
on the circuit diagram, you never do this.
No problem happens,
right? On the circuit diagram, you don't do this. You if you must, you could like do this, right?
Yeah.
This is just like a circuit notation, okay? But physically, that's no problem because they just cross in free space. Yeah, that's no problem. Okay, but I'm a little curious about this pi. Okay, this pi gate, this Z gate, how do you implement it? So you say that we could put a mirror here, put a mirror here.
It will be just, in my method, it's just when we apply beam splitter. So it's just we have input here, output here, here. What we do is then put thing here.
Yeah.
So this is a pi.
Yeah. Okay. So right. Hey, thank you.
So everything will flip to the other side.
Yeah. Okay. So I agree. Just because we're recording this and this we'll have a screenshot of the board. So just to be consistent, I need to erase your note, but I appreciate your note. But you're right. So we put here a mirror and here a mirror, so it goes this way. So that means we need to put all the stuff we have here, right? And then here we do the same thing. So we put it here. The light goes rerouted here.
There, the easiest thing is just put the detector above. We just need to put detector either horizontally or vertically, right?
Right.
If you are putting one detector.
Right.
So just put the detector in the vertical direction, then we don't have to care about the pi.
You mean we can still remain working with this?
I mean, here we can either detect this one or this one, right?
Yeah.
So if you're putting detector here, then the pi, you don't need detector.
Sure. Don't worry about this. Sorry, I was not. How about this?
This one we can change the whole thing to this side.
The whole thing to the side. Yeah. Okay, so this also flipped, right? And you were saying that in principle, I need to add another mirror here, and then put detector here.
Yes.
But if we just detect
the
vertical, then I don't need to worry about it. Yeah, I think that's a good idea. Okay, cool. So you see, this is it's quite involved. A lot of mirrors involved.
Yes.
Okay. The curious thing is in our experiment, we don't have this. What we have is a microsect interferometer. So the physical implementation of the Deutsch algorithm in our lab is this. Okay, and then you do this mirrored, this mirrored, and here, of course, you can have a different angle. So one is this, and the other is 45, right? So this is mirrored. This is mirrored. And then you're looking here. Yeah? All right. So what kind of bothers me, and I have not figured this out, is how is this equivalent to
No, this is equivalent because until here it's all right?
Yeah?
Then we need to reflect this to this side. That's what this mirror doing. This pi.
Okay.
That's this mirror doing.
Yeah?
So it passed through these 2 times. So I think we need to put this at
20,
half.
Yeah?
Instead of 45, 25. So this come back here.
Okay, let me write down. So you're right. So this is 22.5. Okay.
So this side come back here. So that's then it's equivalent to going to here and dictating. And this side is same. We are using the 2 mirrors to get into this direction. Instead of going this, here we are switching this to V. Here we are doing to minus V. So this pi will go to V.
Oh, okay. So this is just this is the minus, right?
Here it is H. Here there is a pi. So when it comes back, it's
Yeah.
minus H.
Yeah. Let me see if I get what you said. So you're saying this together is the Hadamard.
No, this and this.
Oh, okay, right.
This is this.
Right. So these three are the same. Yeah.
This 3 combined is this 3.
Yeah.
But this we are again using this one.
Hold on a second. And
instead
how about
of the 2 beam splitter,
uh-huh,
we are using the same beam splitter again.
How about this guy?
Yeah.
You don't care about because you're putting the detector in the vertical.
The thing is, when we are coming here, this is minus V. So what here beam splitter we did to directly V. H goes to H and V. Here it goes to minus V. Then we do the pi. So here it goes to V.
Let's see. So this doesn't matter. You don't need this, right? You don't in this construction.
No.
You don't need these two.
No.
You don't need these 2 mirrors, right?
No.
Right, because they are here. Okay. So you're saying that these 2 mirrors can be done away, right? And this is responsible for this pi here. And how about this? This also reintroduce a pi.
No, that's because here we are directly using the beam splitter to go to vertical direction.
Oh, I see.
Here we are going to minus V.
Okay. So,
So
this
we had
this
to change
cancel
to
out
Z
the
gauge.
minus B.
Yeah.
Okay, I
So
see.
instead of this, we are going minus.
Yeah.
Like
I see.
if
I see.
change,
Yeah.
This is the beam splitter that we are introducing.
I see.
So
Yeah, I got you. Okay, I got you. So here we don't really have a Hadamard gate, like a pure Hadamard gate.
yes.
It's more like Hadamard gate uh, in addition, like combined with I get what you mean. Okay, so so you're saying that this is going down is minus V and going up is plus V.
Yes.
Okay.
So
and
both
and,
sides.
and this gives you the desired phase, and then this is just this,
Here we
and
need
then
to come.
and this you don't need because you are not detecting here,
Yes.
and you're just detecting here. Okay, so this is rather
in like these two Hadamard gate are the same beam splitter, and in the first time we used two mirrors to get the Hadamard gate.
Yeah. Okay, I got you. All right, thank you very much. That's very helpful because I don't understand how this works, but thank you for solving the problem. Okay, I think this is great. Okay, good. All right, so that's the end of the lecture, and unsurprisingly, it takes super long, but even though there's only one person, you still have the chance to win the bonus. Okay, and this is gonna be a pretty easy question for you, I believe.
I hope so.
I think it's gonna be very easy. Given that you are teaching me how to do this, I think this is gonna be very easy for you.
No, I'm also learning this.
I think this is great. I learned stuff too. It's the most rewarding thing for a teacher is that he learns from his student. I'm not kidding. Like, it is so boring to having to give all the time. Sometimes when you receive, that's encouraging too. All right, so quiz number 1. Can the Deutsch-Jozsa algorithm work with the control qubit set as 0? Okay, yes or no? You can, because I need to leave pretty soon, so you can start choosing your answer. And can the Deutsch algorithm be used to find out if all outputs are equal to 1? Okay, so that means this is just to be more specific. That's what I mean here.
So first question I have the problem is
Choose
when
side.
the math it should say 0, but I can think about some ways to define the gate such that it also works for 1. But at that time it doesn't work for 1 state. Yeah, so I'll go with 0. I don't want to make it complicated.
If you put in a, okay, so you go with 0, right?
Yes.
All right, then debate with me. You're wrong. If you put in additional gates, then it's not the Deutsch.
No, not
algorithm.
additional gate.
Uh-huh.
The gate we put means in the optical setup we define the gate such that it comes like H is this, V is this.
Right.
If we put the opposite, I need to make some changes to the gate such that it works for H as this one and V as this one.
Okay. And what you're saying?
I can make such thing, but
but the control qubit here is V.
Yes.
Right? Oh, sorry. A control qubit set at 0 will be V. Okay.
Yes.
And then you're saying that you could do
means
magic.
If we means it's our choice to take whether H or V is 1, right? Then we set the gates according to that.
Right.
So it's a choice we are making, which is 1, which is 0.
Sure, but it needs to be consistent.
Yes, that's why if one always give the results, then I would say it will not work if you set 0. That's why I stand in the no. But we can switch it, but there's some changes we need to make in the math. Yeah, but I'll go with no. So it's okay.
I don't know. I think if you change that to 0, right? If you just change the definition, okay, it's like you change the basis, right? Yes. And all the other metrics change as well. Of course, you're effectively still working with 1.
Yes.
Okay.
That's why,
when I say 0, that means that means nothing changed, but only the. It's not like a base change. It's you literally change that.
If 1 is what we have only take 2 states and 1 state is a control state 1. Yeah, then I agree with this. Like it will not work. So.
Okay. All right. Oh, okay. You're right. Correct. All right. So 1 point.
Yes.
Oh, you need to choose your yes or no first.
Yes.
You choose yes. Okay.
Explain
to me why.
Does this question means we are putting 1 here and we get 1 here? Or just 1 here? We are not defining what the state here.
No. This question means. So I'm not asking how you read. Okay? I'm not asking what you put. I did not specify what you put in or what you read.
Okay.
I'm just saying that can we find like exactly so we can find this, right? But can we find it is this case? You see what I'm saying?
Yes.
So instead of a global property, can we find it's also the local property at the cost of one run, right? So this is, you see, this equal to 1, this equal to 1, that requires 2 runs.
Yes.
Right?
I will go with no.
So this is a different question, right?
Yes.
So can Deutsch algorithm be used to find out about the local property of the function?
What this means.
That just means this.
Yeah.
Okay.
So no.
All right. Are you sure?
Yes.
Okay.
For local property, we need to find each case.
Congratulations.
Thank
right?
you.
Because this only run once, right?
Yes.
It's supposed to run once and give you the answer, right? So to find out the local property, we need to run it twice.
You give the relation.
Like in principle, we need to run it twice, and so the point is all the algorithm leverage the power of superposition to find out the global property, and it's the global property they can give you, not the local property. The local property still depends on the individual inquiries, I think.
I don't know how.
I'm not saying that I'm not saying this can be used to find. I'm not saying this can be used even with many runs. I'm not saying this can be used to find this. I'm just saying in principle this takes 2 runs, 2 inquiries, and in principle the algorithm, the corner algorithm requires 1 run to give you the global property. Okay, so you see like the number of runs are simply different.
Yeah.
Okay, and
I
then
think we need to remove the both edge gates to find this property.
You need what?
We need to remove both the edge gates.
Oh.
Then only we can find this property.
Then okay.
Still, we cannot do it in 1 run.
Yeah. All right. So great. Thank you. Good exercise.
Thank you.
All right. Cool. All right. I will need to go now, but I will come back and check on you.
Okay.
In the lab.
TA will be there.
Oh yeah, TA will be there. Yeah, he's there. Could you do me a favor and turn off the AC? Thank you.